Greetings, folks. Today we're going to talk about the history of the atomic structure. I'm recording this PowerPoint. I'm going to do it in 3 parts because it's a rather long PowerPoint. Okay? Ancient philosophy. Where did this all begin? Aristotle and Democritus, more than 2,000 years ago in ancient Greece. Aristotle believed in the 4 elements: earth, wind, fire, and water. Notice earth, wind, and fire here is highlighted for a link. Run the PowerPoint yourself and see what it does. Democritus believed that matter was made up of small particles he named atoms. Aristotle and Democritus used observation and inference to explain the existence of everything. At least they tried to. That's one of the things the ancient Greeks did. They didn't so much run experiments as they sat around and thought a lot. Aristotle, Democritus. I guess they just didn't have their cell phone cameras with them that day. Okay, alchemist, European scientist, 800, 900 years ago in Europe. Their work developed into what is now modern chemistry. Alchemists were trying to change ordinary materials into gold, and there were a lot of alchemists trying to do this. Here are the symbols used by the alchemist. We have antimony, copper, lead, gold, magnesium. It's amazing to me that this long ago they actually have figured out these elements. If you notice that iron is the same symbol used in medicine for the male form, right? Interesting, if you go back into the history of chemistry, a lot of alchemy was based on bodily fluids. And that's all I'm going to say about it. Atomic theory. Here we go. John Dalton, 1808. England. Described atoms as tiny particles that could not be divided. We, of course, know now atoms can be divided. They split them all the time. He also thought each element was made up of its own kind of atom, which it is, right? Protons define the element. He built on the ideas of Democritus in ancient Greece. Dalton's atomic theory. Know this. Let me repeat. Know this. Elements are composed of extremely small particles called atoms. All atoms of a given element are identical. Atoms of different elements are different. Compounds are composed of atoms of more than one element, and we now know that these compounds are different atoms bonded together. Number 4, a chemical reaction involves only the separation, combination, or rearrangement of atoms. The atoms themselves are neither created nor destroyed. John Dalton, handsome fellow, looks very thoughtful there. Discovery of electrons. J.J. Thomson in 1897 in England. Thomson discovered that electrons were smaller particles of an atom and were negatively charged. Thomson knew that atoms were neutrally charged, but he was trying to figure out if there were opposite charges attracting. Couldn't find a positive particle. Cathode ray tube. This is actually what made the old tube-style televisions work. What you have is you have a glass tube with a vacuum in it. Nothing is in it. On one end you put a positive charge, on the other end you put a negative charge, very high voltage. The voltage, and what is electricity but electrons, actually jumps the space between the positively and negatively charged, and you have a beam of electrons. Okay? And what's very cool about this is, since the electrons have a charge, the plates can steer the beams. Let's take a look at a video showing this. Okay? Here you have the cathode ray tube. It's vacuum, no gas in it. Here is your high voltage generator. Positive on one end, negative on the other. Start it up and you see a beam of electrons. Since electrons are negatively charged, if you take a magnet, you can deflect the beam, right? The negative end of a magnet deflects the electrons away. If you turn the magnet around, the positive side, it will attract the beams. See, turn the magnet around, and now we're attractive. Positive end of the magnet is attracting the negative electrons. J.J. Thomson. Discovery of the mass of electrons. This is fascinating. Done by Robert Millikan, 1900s, at the University of Chicago. He developed the method of measuring the charge of an electron, actually in electron volts, and by extension the mass of the electron. Due to the close relationship between magnetism and electricity, it was deduced electrons must have a measurable charge. Okay, the Millikan oil drop experiment. Here's how this works. You have an atomizer, which simply sprays a fine mist of oil onto a plate with a very tiny hole in it. A few of those oil drops will drop down between the plates, and these plates are charged positive and negative. Then an ionizing source, giving off electrons, will actually put electrons onto this oil drop. Telescope here to observe the oil drops, but now that you have electrons on an oil drop, by varying the current of the two plates, you could actually make the oil drop float, move up, move down. And what Millikan noticed was the amount of electrical charge was a ratio. So he was actually able to deduce by the charges that were on the oil drops and how many electron volts it took to hold up the oil. He could actually work back to the charge of the electrons and the mass of the electrons. Robert Millikan, nice boy from Chicago. Discovery of the neutron. James Chadwick, 1932. University of Cambridge in England. Determined there was a subatomic particle with mass but no charge. In other words, the neutron. Form of radiation emitted through experiments such as this was inconsistent with known types of radiation. Here's an illustration. We have a source of alpha particles. Alpha particles are simply loose protons from a radioactive source, some radioactive material decaying. Aimed at a plate of beryllium, the protons actually replaced neutrons, and the neutrons were set free as a beam of radiation with no charge. Okay, that's how it was determined that there were neutrons. There was a beam of radiation, but it was not deflected by an electromagnetic field. And James Chadwick. It's amazing these guys did this work when they did. Atomic Structure 1. Ernest Rutherford. 1911 in England. The gold foil experiment. Conducted an experiment to isolate the positive particles in an atom. He decided that the atoms were mostly empty space, but it had a dense central core. He knew atoms had positive and negative particles, but he could not decide how they were arranged. Here's Rutherford's gold foil experiment. Now, until this experiment, J.J. Thomson, of the cathode ray tube fame, thought the model of the atom was a plum pudding model, that overall the atom was positive with the negative electrons embedded in it. If this were true, then you should be able to shoot alpha particles through an element, and you would see some slight distortion of the alpha particles going through the atom, but they would mostly go straight through. When Rutherford ran his experiment, what he found was every now and then an alpha particle would be deflected at an odd angle onto the detecting screen. This detecting screen was essentially photographic plate, so that when an alpha particle hit it, it would expose the film. What he found was Most alpha particles went straight through the gold foil, but some of them were deflected at odd angles, some of them even coming right back at the emitter. The result of that was he deduced that an atom was mostly empty space, but had a small, very dense core or nucleus. It was the alpha particles being deflected by the nucleus at these sharp angles that caused Rutherford to deduce that atoms had a small, dense nucleus. And there's our man, Ernest Rutherford. Okay, this wraps up part 1. Part 2's up next. Thank you.